Well, thank you very much. So I'm going to be talking today about a few different things. I'm going to be talking about the value, I believe, of a liberal arts education, as we're here at a liberal arts school, the value of what I call basic science, and of course, the value of sea slugs. This will be the star player a little later on in the talk. This is the lion-hooded nudibranch. Swimming or dancing, depending on your perspective, and we'll get a chance to see that a little later. But I actually want to start by stealing a page from Eric's talk. I learn a lot from Eric because he knows how to teach. And I actually want you to pull your cell phones out. And I want to get a sense from all of you here. Since we're here today at a liberal arts college, some of you may be affiliated with the college, some of you may not, right? So text 50446, and then in 5 words or less, what does a liberal arts education mean to you? And text it to 37607. And in real time, we'll get to see some of your responses for what you think a liberal arts education is. Now, there is a cap on this. Only 40 of you can respond, so at some point, if it fills up, you may get a message on your cell phone saying, sorry, survey's full. We can only be so hopeful that we have that much participation. And it also depends on our internet connection. I have the privilege of teaching, learning how to think. Oh, I like that one. Balance of art and science. Learning how to think is something that I think I will return to in a second. Now, if I was really adept at this, what I would do is build what they call a cloud tree or something, where we could sort of put common themes together. Somebody's testing. It works. Liberal education of art, learning to open your mind. Interesting. Creativity, better reading and analytical skills. Stretching your mind, learning to open your mind, so connections there. Thoughtful, global perspective. A little knowledge of everything. Some good answers here. Thinking and art. Knowledge for its own sake. I think we can clearly see there's some common themes here, but there's also a lot of diversity here, right? And I think it's because liberal arts education is many things. And I would say it is all of these things. But in the interest of time, I'm going to cut us off here now. Thank you for your responses. And I'm going to put up here something that some of you actually said in slightly different words. And this is, so I think liberal arts education is many things. But for the relevance of this talk, I'd say that it's really education for education's sake. Learning just to learn. And, I'm a biology professor here, but I was not always a biologist. I come at biology from an interesting perspective. And so I have a prior background as a musician. I was a classically trained violinist. I very much appreciated Chris Kavanaugh's performance early this morning, where I never got to play an electric violin. And I also did much in the way of theater, and even managed to sneak up on stage recently for a stage reading of Inherit the Wind last February with our president over here, Michelle Perkins, who has a theater background, and our vice president of academic affairs, Mark Watman, who introduced us earlier today. And so I come at it from this background. I also spent my 20s doing dance and choreography, and came across a little snippet a little bit earlier as I was digging through the archives of me dancing way back when. Those were the days. I had so much fun with that piece. No, thank you. But I'm not a dancer or a choreographer now. I'm a biologist. And I'm very interested, as Mark said, in the nervous system and how the nervous system produces behavior. And I think the fact that I come at science from a different history and a different perspective than some scientists, not all, gives me a different perspective sometimes on scientific questions or scientific problems that I'm trying to get at. And I think that a liberal arts education does this, right? We learn many things. People talked about learning a little bit of a lot of things. We learn how to think. And let's not talk about me. If we think about some other famous scientists that we all know, right? So I pulled out an example here. Carl Sagan, astronomer, cosmologist, very famous for his ability to sort of relay astronomy to the public through his Cosmos television show. But he also was an artist and a writer. He wrote novels that even got made into books. Okay, so he came at astronomy from a slightly different perspective. If I was to ask you, name a scientist, a majority of answers probably come up with this one, right? Albert Einstein, the father of the theory of relativity. But Einstein was much more than a mathematician and a physicist. He was also a musician. He played the violin. He played the piano. And he was also a great source of quotes. And one of my favorites is that the value of an education in a liberal arts college is not the learning of many facts, but the training of the mind to think something that cannot be learned from textbooks. He says it much better than I can for what a liberal arts education really means. Now, I said about to talk about the value of liberal arts education, but also the value of basic science. So even the theory of relativity, at the time that Einstein did this back at the turn of the century, was very basic science. And I would argue that basic science is science for science's sake. Okay, doing science for no other reason than just trying to figure something out. Now, when you hear about on the news all the latest scientific advances, and a lot of them are very good, this is what we would call translational science or applied science or the commercial application of science. But that is all built on a much larger foundation of basic science. They never would have been able to do those studies if it wasn't for other people who had been doing work just trying to figure something out. And I want to give a great example of this for you, and I'll lead into it with another quote from Carl Sagan. Our species needs and deserves a citizenry with minds wide awake and a basic understanding of how the world works. So the example I'm going to give, because it leads very nicely into the last part of my talk, is green fluorescent protein. And so Osamu Shimomura, back in the early 1960s, was very interested in jellyfish, of all things, and specifically bioluminescence. And he came over to Friday Harbor Laboratories over on the west coast of the US, which is a great place. I've been there myself to do research. And he was studying the local population of jellyfish there and was very interested in how they bioluminesced and how the green fluorescent proteins that were there played a role in this. And he was just interested in how they did it. But in the ensuing decades, researchers were able to sort of connect the dots and take work that he did and others and say, well, we could take this green fluorescent protein, we could attach it to chemicals, or we could get it genetically express it in organisms, and now we can get certain proteins, certain structures, or certain cells to light up, and we can now see them. And this was such an important advance that they gave the Nobel Prize in Chemistry to Osamu Shimomura and others in 2008 for his work in developing this. But at the time he did it, it was just basic science. He wasn't trying to do anything other than understand jellyfish. Now, I use this work myself, right? So this here is an outline of a sea slug brain, and specifically the one I showed you on the first slide. And it's lit up nicely green here. All those little circles that are green, those are actually labeled with something like green fluorescent protein. Those are all neurons that contain serotonin, using technology that stems from basic science that Osamu Shimomura did back in the early 1960s. So now, to talk a little bit in the last part of my talk here, as I said, I'm interested in the nervous system, how it affects behavior, and lately I've been studying a lot about circadian rhythms. These are sort of the 24-hour rhythms of behavior and physiology that almost all organisms exhibit. You will stay awake for a certain while today, and then you're going to go to bed, then you're going to wake up tomorrow, and you're going to do it again. And there's this 24-hour cycle, and this 24-hour cycle is actually controlled by an internal clock. And we know that because if we took all of you and we put you in a dark cave and we left you there without any light cues for an extended period of time, you would still be active for 12 to 16 hours a day and then sleep for 8 hours a day, and that cycle would continue. Okay? And you just use light to reset it. Okay? So jet lag, right? You fly a few time zones. Your internal clock gets out of sync with the external cues. You get all weirded out until everything gets back in sync. So we're looking at circadian rhythms, and we know a lot about the behavior for centuries, and we know now, in the past few decades, about the molecular mechanisms underlying it. Okay? And basically, it's just a negative feedback loop. Certain proteins made, build up, they inhibit their own production, then the levels go back down, inhibition's removed, and the whole thing starts again over 24 hours. But what we don't really understand, though we understand that, and we understand the behavior, is how the two are connected. How do you get from all this complicated gobbledygook up here into 24-hour cycles of behavior? And this kind of a big black box that we don't know a lot about. So we can study this, of course, in mammals, in humans, and whatnot, but the problem with that is that we are extremely complex. Our brains have a lot of neurons, and each of those neurons is talking to anywhere from 1,000 to 10,000 other neurons. Mind-blowingly complex. So, the value of sea slugs. So sea slugs have a brain orders of magnitude smaller, about the size of your little pinky fingernail, with an orders of magnitude less neurons and orders of magnitude less complexity. But they still have many of the same behaviors that we do, and we might be able to understand some of the neural mechanisms underlying these behaviors because it's much of a simpler system. So the lion-hooded nudibranch that I showed at the beginning, well, I said it dances or swims. So this is the critter, and this is the head region right here, and it does this alternating bending from left to right. I'm not going to dance it for you, but this obviously is not going to get it from point A to point B very well. Okay, but it has evolved to fit its little niche, and this is a very useful behavior for it to get it up off of a substrate, away from a predator, out into the water column, etc. Now, we know a lot about the locomotion in this animal, the dancing. We also, that's the brain, again, of this animal. And would you believe that only 4 neurons control that entire behavior? 4. There might be more, but 4 are sufficient to control the whole darn thing. And not only do we know that there are 4, we know where they are in the brain, we know how they talk to each other. So we know how they communicate, how the circuit is built. And, like I said, we know a bit about behavior. So we know that they're much more active at night than they are during the day, and that this will continue in constant darkness. So this gives us an opportunity to potentially explore how circadian rhythms might operate in this animal. So another thing we've done is we've actually sequenced the genome for this animal. Sequencing technology has come so far, you can, within the next couple of weeks, sequence your own genome for a couple of grand. And so we can do the same thing with these organisms. And we can sequence their genome, which allows us to find the specific circadian genes in this animal, build antibodies to those particular genes in this animal, and then, like the picture I showed before with serotonin, to say, all right, where are the circadian genes in the nervous system of this animal? And find the clock. And that's what we're working on. There's preliminary data on that. So what do we want to do with it? Well, if we can find the clock in this animal, then, and we know a lot about the circadian behavior, we know the circuit that controls the behavior, we can connect the dots in a way that has never been done in any other organism by looking at a simpler system, by doing basic science. We are not curing cancer here. I will not solve the problem of jet lag, right? I'm merely trying to understand how a sea slug dances and how that is controlled in a circadian behavior. So I hope that you've learned a little bit about maybe the value of a liberal arts education, the value of basic science, and of course, the value of sea slugs. Thank you.